Okay, in our effort to sketch a asymptotic Bode plot, there's a couple rules, and this is kind of like the root locus. It's easier demonstrated than it is to look at the rules and follow the rules. Once you understand what's being done, it's pretty easy. But let's go through a few rules first, and then we'll proceed with some examples. So here's the rules for sketching an asymptotic Bode. And first thing we want to do is we want to factor. And this is what we do most of the times. We'll take our transfer function and factor it. Now, while I'm here, let me mention that you can do a Bode plot on the open loop transfer function and the closed loop transfer function. Unlike the root locus, remember the root locus only made sense for the open loop transfer function. The Bode, both the open loop and the closed loop have meaning. We will be working primarily on the open loop transfer function, the open loop Bode, to reshape the closed loop Bode. But we can talk about both of those. So be sure which one we're talking about. If I ask you to plot a Bode of a closed loop system, say, do you want the open loop or do you want the closed loop? I will try to be mindful of that and ask specifically, but you should be aware also that you can both apply. Okay, so anyway, we're going to factor this, and whatever the transfer function is, we factor it into free integrals, free s's, first order terms and second order terms. And we can do that by hand, or you can simply do a ZPK in Bode or in MATLAB and get it. And so then what we're going to do is we're going to we're going to start with a magnitude plot. And we're going to find the slope, which is determined by the number of free integrators, and that we find up here. If we have a free integrator or an s determined by the number of free s's. If we have an s in the numerator, a derivative term, then the initial slope is going to be at 20 dB per decade. Okay, that doesn't make much sense right now, but hold on to that. And then if we've got a free integrator, an s in the denominator, it's going to be, the initial slope is going to be minus 20 dB per decade. Okay, all right. So hold on to that. Put that in your back pocket. Then what we're going to do is find the DC gain with the DC gain of the transfer function with the free s's removed. We're going to remove the free s's, and we're going to find the DC gain. And the DC gain is just taking s is equal to 0 and finding out what it is. With that, we're going to find a point on our plot at omega equal 1 and DC at the DC gain and with the initial slope. Okay, all that sounds really messy, but it's not. And then we're going to just move along and add slope or subtract slope at their breakpoints. Okay, so we're going to start just with some first order systems. Here we've got a 0 in here at A, and at the break frequency of A, we will add 20 dB per decade. And here's a pole at A, and so at the frequency A, we decrease the slope by minus 20 dB per decade. Okay, so I know that sounds really weird, and we're going to stop there. We're just going to do some single first order poles and zeros and initial slopes, and we'll do a few examples like that, and then we'll come back and we'll attack these second order terms after that. Okay.